Hello everyone, today we're looking at forces in two dimensions and two-dimensional forces. We've seen before when we see a vector like this that is two-dimensional, it's neither on the x-axis nor the y-axis, we need to break it into components, and those components are independent of each other. So let's take a look at an example. We have a mass that's being pulled along with some two-dimensional tension as it travels to the right on this horizontal surface. And all the forces here are given. They're given with values, but I would like to just draw a quick free body diagram of the scenario. We know a free body diagram, we represent the object as a dot, so that is a dot representing the center of mass. Looks like this object has a weight that is straight down. In this case, it's 90 degrees. It also, since it's on a surface, has a normal force. But I want you to know that notice that normal force is not quite as large as the weight, right? I mean, a lot of times we've seen the normal and the weight were balanced. But in this case, because we have a two-dimensional tension and there's a vertical component of that tension that allows the normal force not to have to be as large as 90 newtons, right? It'll be the sum of these upward forces that are going to equal 90. So we have that tension. It is like this at some angle that we're going to find. And then the last thing, we have some resistive force, whether that's drag or friction. It hasn't been made clear, but let's just call that a friction force to the left. And since it is sliding, let's call that a kinetic friction value. So I wanted to do this free body diagram to show each of the forces and how I consider the magnitudes and the size of the arrows. For example, I did not draw the normal force as large as the weight because I knew there was an additional component to the tension that will add to the normal force to balance with the weight. But one thing I want to mention for your AP exam, this free body diagram is complete. I wouldn't want to do anything else to this free body diagram. I also don't want to show components on my free body diagram. So if you draw components, they're going to consider those to be additional forces, and then you're going to get your free body diagram marked wrong. So here's my free body diagram. Those are the four individual forces that are acting on this object. Now on this image, I will go ahead and take tension and break it into a horizontal and a vertical part. So I don't want to do that on my free body diagram, so just be careful with that. But now I can sum my forces and set up the net force both horizontally and vertically. Let's unpack this information a little bit first. It says that this object is increasing speed while traveling to the right. We have those motion lines there. So if it's traveling to the right and its speed is increasing, it means the acceleration must be to the right. And since the acceleration is to the right, it means our net force is to the right as well. So one thing I know is vertically the forces are balanced because we're moving on this horizontal plane, and horizontally the rightward forces are going to win by 20 newtons. So that allows me to determine the vertical component of this tension. In order for the vertical forces to be balanced, I have an up 50, I will need an up 40 newtons for a total of 90 newtons up and 90 newtons down. And I could just write the sum of the vertical forces is 50 plus the vertical component of the tension minus 90 because it's downward, and that should equal MAY. And since this object is not accelerating vertically, we could set that equal to 0. So if I needed to prove that the tension was 40 newtons, I would do it this way, and I would move the 90 over and then subtract 50. So the vertical component of the tension is 40 newtons. I can also find the horizontal component by summing the horizontal forces. And the only two that I'm seeing are the horizontal component of tension and the 10 newtons of friction. So I'll say horizontal component of tension minus friction is equal to MAX, or in this case, F net, the mass times acceleration. So we know we want to find FTX. We know the friction is 10 newtons, and we know the net force is 20. And I've taken care of the direction by having the horizontal component of tension as my positive. I knew that was going to be the winning force, and I subtracted 10 newtons because it was to the left. So I end up with a net force in the positive direction. And if I want FTX, I'm just going to add to the other side, and the horizontal component of tension is 30 newtons. Okay? So now I've got both components of that tension, and if I want to find the actual tension, like the real tension that we would experience in the string, is this two-dimensional hypotenuse. So if I wanted to find that hypotenuse, if I know two sides of a right triangle, then I can use Pythagorean theorem. So I can do 30 squared plus 40 squared and take the square root, and it turns out that my tension is 50 newtons. Okay? The last thing I want to determine is the angle. At what angle is this string or rope being pulled? And since I've got the opposite and the adjacent side, I can use an inverse trig function to find that angle. So I know that the tangent of theta is the opposite over the adjacent, and the side across from theta is our opposite side. The side touching theta that's not the hypotenuse is the adjacent side. So tangent of theta is equal to 40 over 30, or opposite over adjacent. And if I want theta, I'll do an inverse trig function to release theta from that tangent. So tan inverse of opposite over adjacent, or 40 over 30, should give me my angle. So just making sure that you are in degree mode. So hit your calculator, hit mode, and make sure you have degrees selected and not radians. But I'm going to do an inverse tangent of 40 over 30, and I'm coming up with about 53.13 degrees. Okay, so I found both of the components of the tension, which allow me to resolve the actual two-dimensional tension. It's 50 newtons at an angle of 53.13 degrees from the horizontal. Okay, so anytime we see those two-dimensional vectors, we know we want to break them up. Things get a little bit interesting when we look at inclined planes. So if we're on a ramp, I want you to consider the direction of the acceleration for something like this. I have a frictionless cart that's going to roll down the hill, so the acceleration would be in this direction, parallel to the ramp. And you know, if I were to draw the free body diagram for this cart, it would of course have Fg down, and it would also have a normal force that is perpendicular to the ramp. And I'm looking at those two forces, and in a typical coordinate system where x is horizontal and y is vertical, in that coordinate system, the normal force is two-dimensional, just like the tension that we had on the last slide. So I might want to break that normal force up into components. But I want you to notice what that's going to do to our acceleration. Our acceleration in a regular coordinate system is also two-dimensional. It's not on the x-axis, it's not on the y-axis. So I really would inconvenience myself by using a traditional coordinate system and breaking the normal force into components. Instead, what I'm going to do is I'm going to use a non-traditional coordinate system. And what I'm trying to do is end up with just a one-dimensional acceleration. Now, a coordinate system still needs to be 90 degrees, still needs to be perpendicular. So how can I take this x-y coordinate system and allow the acceleration to be one-dimensional so that I don't have two components to the acceleration? Well, I'm going to take the origin of my coordinate system and I'm just going to tip it. I'm going to angle it so that I have, instead of horizontal and vertical, I have one axis that's parallel to the ramp and one axis that's perpendicular to the ramp. And in this new coordinate system, my acceleration is one-dimensional. It's on the x-axis. You'll also notice that my normal force is one-dimensional in this coordinate system. It's right on the y-axis. So in my new coordinate system, it's actually Fg that is two-dimensional, that's not on the x or the y-axis. So I'm going to go ahead and break Fg into components in this coordinate system. And I have one component that I call the normal weight, and that's because that's the component of the weight that's balanced with the normal force. And then I have what I call the downhill weight, which is, well, it's the part of the weight that's downhill. It's trying to make the cart speed up down the hill, okay? So with those components, I have one component of the weight that's perpendicular to the ramp and one component of the weight that's parallel to the ramp. And in this coordinate system, it makes things a little bit easier because the sum of the forces in the y direction, which is perpendicular to the ramp, is going to be 0 because this cart only moves down the ramp parallel to the ramp, and then the sum of the forces in the x direction or parallel to the ramp, that's going to equal ma. So I've got this acceleration, now it's one-dimensional. In the y direction, there is no net force. The forces are balanced, they're in equilibrium. Okay? Okay? The one thing I think students find challenging is, okay, here's theta, it's the angle of the ramp, but I haven't trapped it anywhere in my right triangle. So how do I get this theta and put it into the triangle for the components of my FG? And the way that I do that is I really look at similar triangles and anywhere that I can find perpendiculars, anywhere I can find 90 degrees. So what I'm going to do is I'm going to take this force of gravity, I'm just going to move it down to the ramp. Instead of to the middle of the cart, I'm just moving everything down so that it's touching the ramp, okay? And hopefully what you notice here is that vertical FG, if I extend that line, it makes a right triangle with the horizontal. And if this angle is theta, and we have a right angle right here, 90 degrees, the angle in this upper part of the triangle is not theta. So let me just call it something else. I'll use the Greek letter phi. But one thing I know about triangles is that the angles inside have to add up to 180. So because of that, if I have a right angle here, I know that theta and phi actually add up to 90 degrees. So anywhere I see a 90 degree with one of these angles, I know the other angle is either theta or phi. So I see a right angle right here with the ramp and the component of gravity that's perpendicular to the ramp. And I've got this inner angle to be phi. So this angle that's actually captured by my right triangle has to be theta, because again, I know that theta and phi add up to 90 degrees. So with that information, I'm able to now identify the sides of my right triangle. For the force of gravity, this component that's perpendicular to the ramp is the adjacent side. And for the force of gravity, the component parallel to the ramp is the opposite side. And using my trig functions to relate each side to the hypotenuse, or in this case, the real force, right? The weight is the actual force, the hypotenuse of this right triangle. I'm trying to find the components so that we can sum the forces in the x and the y direction. So my downhill weight, since it is the opposite side, that would be Fg sine of theta, and the perpendicular component, or the normal weight, would be Fg cosine of theta. Now, there is a little mnemonic that I like to use. As long as the angle is given of the ramp, so from the horizontal, then Fg sine of theta starts with an S. I think of that as the sliding part of gravity, the part that's actually trying to bring it down the ramp. So in a pinch, if you can't go through that geometry quickly, we can remember that the downhill weight is going to be the sliding weight, the sine of theta. And then the normal weight will be the cosine, because it's the adjacent in that right triangle. Okay? So we'll take a look at an example with the sliding and the normal weight. A 5 kilogram frictionless cart placed on an 11-degree incline is going to slide down. I'd like to determine the acceleration of the cart. So I know that there are only two forces here. There is the normal force, and I'm not doing a great job making it perpendicular to the ramp there. So let me try that again. So we have the normal force that is perpendicular to the surface, and then we have the weight of the object straight down, Fg. And again, I know the acceleration is down the hill like that. So instead of a traditional coordinate system where we have x and y horizontal and vertical, I'm going to take that and I'm going to tilt it so that I have one axis parallel to the ramp and one axis perpendicular to the ramp, and it will be Fg that needs broken up into components in this particular coordinate system. So I have the normal weight and I have the downhill, or the sliding weight. And from the last page, we know that angle right there is theta. Okay? So I've got Fn and Fg. It is the force of gravity that I'm going to break into components. From the sum of the forces in the y direction, I have Fn, and then I have the perpendicular component of Fg, so I'll just say Fg perp, and that has to equal MAy, but perpendicular to the ramp, nothing exciting is happening, it's in equilibrium, so I really know that Fn is just equal to Fg perpendicular. But again, that is our normal weight, or our Mg cos theta, because that is our adjacent side of that right triangle. And then from the sum of the forces in the y, we know that the downhill weight, which is Fg parallel, so I'll use Fg and then a parallel symbol, is equal to Ma. So our acceleration in the y direction is 0. Our total acceleration is now in the x direction. I apologize, I should say x. So the sum of the forces in the x direction is just Fg parallel, meaning the component of gravity parallel to the ramp, and that should equal ma. Well, Fg parallel is just mg sine of theta. So that's equal to ma. I'm seeing here that the mass will cancel. So just like something in free fall, the mass doesn't contribute to the acceleration. Same thing's happening here. This is just an object that's sliding down the ramp. And if we're not considering resistive forces like friction or drag, here the mass doesn't matter. And the acceleration is just g sine of theta. So for an angle of 11 degrees, let's determine the acceleration. So that'll be 10 sine of 11 degrees, and that acceleration is 10 sine of 11, 1.91 roughly, so 1.91 meter per second squared, and that is our acceleration. Okay? It says we should also find the normal force. So we said from the sum of the forces in the y direction, Fn is just mg cosine of theta. So that would be for a mass of 5 kilogram. We'll do 5 times 10 times the cosine of 11 degrees. Oh, jinkies. So let me try that again. Cosine of 11 degrees. So 5 times 10 times the cosine of 11. So what we're seeing here is that the normal force is not quite 50 like it would be on a flat surface. In this case, it's 49.1 newtons. Okay? So we've found both the normal force and the acceleration on an inclined plane, or anytime we have a ramp. It's most likely we're going to want to tilt our coordinate system, because what we're really doing when we tilt our coordinate system is we're trying to get a one-dimensional acceleration. If we have a two-dimensional acceleration, it can make the math a little bit more challenging, because we'll have an ax and an ay, and in order to get the actual magnitude of the real acceleration, we would have to do Pythagorean theorem to resolve those two components. So I think the preferred method is to tilt the coordinate system and force that acceleration to be one-dimensional, and then determine which forces you're going to break into components. Okay? So that is for two-dimensional forces and forces in two dimensions. Thanks for watching.